Thank you, thank you. It's hard to follow such a visual presentation, but I'm hoping these slick graphic design features will be some form of compensation for you. Again, so the topic is optimizing mine soil amendments using waste byproducts. Response surface methodologies, for those that aren't familiar, they're an alternative set of experimental design and data analysis procedures that were developed by the process engineering and manufacturing sector. The intent is specifically for optimization, and they're different fundamentally from the kind of treatment comparison statistics like factorial designs and ANOVA data analysis. So in terms of what I'm going to be discussing is looking at a brief overview of waste byproducts as amendments. Now, Brian Tisch kind of covered the history, which is great, a great boon for my presentation. I'll kind of briefly go over what response surface methodologies are, and then I'm going to apply it, in this case, to amending abandoned gold mine tailings to get those revegetated. So when we're looking at mine soil, there's kind of three fundamental constraints. The first one is that they're fairly infertile. There's very little nutrient and organic matter. And there's physical constraints, either compaction or they're not aggregated, so they don't, the hydraulics are a little off, or they're toxic. So we can amend or mitigate these constraints by adding amendments. In terms of infertility, we can add organic amendments or fertilizer. Organic amendments tend to be a little bit better, a longer-term source of nutrient. With physical constraints, we can break up the material or till it to decompact it. And also we can add organic matter, which helps promote aggregation and improves the soil hydraulics. And especially with mines, and in particular with tailings, is that they can tend to be a bit toxic, either through being acidic or alkaline, or commonly having heavy metals, and that really presents some phytotoxicity to any plants that you're trying to grow in there. So in terms of using waste amendments, I'm not going to spend a lot of time on this, but if anyone's interested, there's a good document that was put together by the Environmental Protection Agency. So they go over a lot of different waste byproducts that can be used and some of the characteristics and how they ameliorate mine soils. But essentially, there's three major groups. So the first group is the organics. So that's just adding nutrients and organic matter, and there's a whole range of organics that you can use. There's municipal wastewater biosolids, compost, agronomic waste, paper mill sludge. There's endless choices, and it's really kind of driven based on what's in close proximity to the mine that you're trying to revegetate. The second major class is looking at pH adjustments, or the alkaline materials. And the intent here is to increase the pH to reduce the metal bioavailability and also improve kind of nutrient retention and availability as well. In terms of waste options, there's fly ashes, wood ashes, FGD sludge, and often these compounds can have a lot of salts or phytotoxic compounds as well. So it's used commonly in conjunction with lime to really boost the pH. The other classes are the mineral soil conditioners. So these are used to modify soil texture. So if, say, you're revegetating a tailings facility and it's a really fine material, you might have to put some coarse material to improve the texture. Or they are added as sorbent materials. So they can, say with the steel slags or the wastewater treatment residuals, not only do they modify soil texture, but they can sorb trace elements, so they're not toxic to the plants that you're trying to grow in there. Now, once you identify what materials are available to you and how you're going to apply them, you got to figure out a rate. How much material do we need to be adding? So with the organic amendments, there's the two common ways of doing it are to meet the plant nitrogen requirements, or to increase soil organic matter to usually around 2 to 5%. But if we're using waste, there can be some imbalanced nutrients in there or a high moisture content. So if you're transporting it to a site, that can really increase your costs. In terms of the pH adjustments, it's usually balanced based on the calcium carbonate equivalents. But like I was saying, the waste can have soluble salts, heavy metals, or boron, which can be phytotoxic. So if you had enough material to offset your acidity, you can still, it can still be toxic to the plant because of those other kind of co-occurring compounds. And with the mineral soil conditioners, it's really site and objective specific, but anywhere up to 100 tons per hectare is usually used, metric tons, megagrams. Again, these can also have salts and metals, which can be phytotoxic. So out of my obligatory text slides, here's some fancy graphs. These are just generic, but I'll show you some real data later. So response surface methods. The purpose is to kind of establish operating conditions that yield an optimum response. So how they differ is that you, rather than doing replicates of 1 or 2 treatments, the way that these experimental designs are set up is to encompass, each experimental unit has a range of values or levels within the operating parameters that you set out. So your responses kind of allow you to develop a prediction model, and that with that prediction model you can create fairly complex surface features or graphs that you can then look for a local maxima or a local minima, and that's you're trying to figure out what the best operating parameters. So in this application, the best or the ideal application rates of your waste amendments to garner the highest vegetation growth or the lowest metal availability. Say. So with the benefits of this is that they're optimization-specific experiments. And in an equivalent number of factors, they require fewer experimental units and hence lower costs than the factorial designs. Some of the drawbacks are that they assume that all factors are important. So anything you put in there, you need to know that it's actually going to be a benefit because you're not comparing treatments to see what's significant and what's not. And it also requires fairly advanced software for design and analysis. So you're not doing this in Excel, but there's a lot of statistical programs that you can do this with. So our particular research objectives are to see whether or not these methods can be applied for optimizing soil amendments. So last summer we did some greenhouse experimentation as a kind of proof of concept, and that's what I'm going to be presenting today. And we have some ongoing field experiments to see if this can be extended to a field context. So with respect to response, what we were looking at is vegetation performance, so looking at maximizing above and below ground biomass, and also balancing the root-to-shoot ratio. So we need a fairly balanced growth between roots and shoots. A plant that sends more resources to the roots, it's a stressed plant, so it's looking for those nutrients in the water, and it's putting more effort into the root growth at the cost of the above ground biomass. So we want that to be a fairly balanced growth. The other response we're looking at is cost. So it's kind of an industrial application, so we wanted to balance our performance with our costs. And in terms of how we're defining cost is both materials cost and quality loss cost. So the materials cost is just the cost of purchasing and transporting those amendments to the site, whereas the quality loss cost is just monetizing the vegetation performance using quality loss functions. So when we're trying to maximize plant growth, say, the closer we are to the maximum of plant growth, then there's very little quality loss cost. But the further we depart from the optimum or the maximized vegetation growth, then we incur quality loss costs and our total cost increases. So now I'm going to discuss the application of this to the Fido Stabilization of abandoned gold mine tailings. So Fido Stabilization is just a fancy term for growing plants in tailings to kind of keep them in place. And it's not growing plants on a cover, it's just directly in the tailings. So this particular site is the Montague Gold Mines. It's just outside of Dartmouth, across the harbor, for those that are unfamiliar. There's been a lot of work done on abandoned gold mine tailings, particularly this facility. There's this publication by NRCan for those that are curious. So this particular location, given that it's close to the city, there's a lot of recreational vehicle use. It's a fairly high health risk hazard. The mine was operated from 1865 to 1940. The gold ore was in an arsenopyrite deposit. They used predominantly mercury amalgamation. So our principal contaminants here are the metalloids of arsenic and mercury. And the pH is around 4.5 to 5.5, which is slightly suboptimal, but it's not down to the pH of 2, or if you were in a pyrrhotite deposit, it would get down that low. So looking at the conditions of these tailings, it's really separated on the landscape. So there's kind of the upper tailings, and then which are a little higher in the landscape, a little drier, and the lower tailings. The upper horizon, up to it's about 10 to 30 centimeters depth, is oxidized. And this is going to be a gross oversimplification, but this is the oxidized zone and the reduced zone. So the arsenic is primarily more available in this kind of oxidized zone, and it's more so bound in the reduced zone. So it's really this upper horizon that we have to amend to get vegetation growing in this material. So we collected two materials from 2 locations in the upper tailings, from 2 locations in the lower tailings, which served as the kind of experimental replicates, and then subjected it to a response surface design. So how we set this out, we had 3 amendments. So we had municipal solid waste compost, so that's what you put in your green bin. The operational parameters that we set were 30 to 100 megagrams or metric tons per hectare, and that was our organic matter nutrient source. We added 0 to 10 tons per hectare of wood chips, and that's just to offset the high nitrogen content of the compost. And steel slag, we added 0 to 35 tons per hectare to sorb the metalloids, and also as a pH adjustment to raise the pH into the above 5.5 range for optimum plant growth. So looking at where we got this material, so our gold mine here, I apologize I didn't update this graph. So I have 2 case studies. We also applied this to the quarry just down the road at the Conrad Brothers quarry. But here I'm just presenting the gold mine. So we had the wood chips just from outside of Sackville. Our compost was our Halifax municipal solid waste compost. And then the steel slag we sourced from the Sydney area. So that, in terms of the cost of amendments, the steel slag is the highest price, just given the proximity. We had to ship it down to this region. But there's a lot of gold mines on the eastern shore, so it would be closer in proximity to the steel slag source. So then we set out our experiment. We grew some plants in it in the greenhouse, had all our various rates of amendments, seeded with tufted hair grass, so that's a metal-tolerant species that can also tolerate high moisture soils, like we have the tailings. Incubated for 50 days, measured above and below ground biomass. We're currently analyzing tissue and soil heavy metals, but I don't have that data to present to you today. And generated the response surface model. Okay? So what I'm just presenting is looking at kind of 3D images of the municipal solid waste and the steel slag amendments. Just for the sake of brevity, I didn't want to go through all of these, but so with the chute biomass, we did find a maximum in this range of, say, around 80 tons per hectare of compost and around 25 tons per hectare of slag. Okay, with the root biomass, we didn't see our maximum. It just kept going up with the more materials we added. But in balancing those two, at the root to chute ratio, we wanted kind of around 1 or around a minimum here. So we also found that in and around where we had the optimum above ground biomass growth. And with our total cost, we had this kind of cost plateau, which is ideally what you'd want. Because the more stuff we add, we're generating a cost, but we want to offset the cost of additions with improved performance. So we found kind of this platform of optimum cost. Now integrating all of the different responses and the combinations of amendments, it's kind of complicated to describe the statistical output, so I'm just only going to present the optimum. So the optimum that we found here was 85 tons per hectare of compost, 24 tons per hectare of steel slag, and 2 tons per hectare of wood chips. So that combination of amendments gave us the compromise optimum of the maximized biomasses, the root to chute ratio around 1, and kind of minimized cost incurred. So in summary, the response surface methods worked fairly well for optimizing amendments in a greenhouse setting. The response surface methods help us, or can be used to improve project performance by avoiding under or over applications of amendments to get vegetation growing in a mine media. But going forward, we need to field validate. So we're looking at putting those optimized amendments out in the field, and then also playing around with some biological inoculants as well to see if by adding a biological inoculant we can reduce the amount of material we have to add. Okay, so I'm just going to acknowledge the partners for this. So we have the Stantec team, Gordon Price at Dalhousie, he's a waste management guy. University of Alberta, there's a land reclamation group out there that's been helping out. And also Mike Parsons at NRCan has been, he's done a lot of work on the Montague tailings and has been a good resource. And our in-kind contributions by Quality Seeds and help through Conrad Brothers and NSERC and DNR. So I'll entertain any questions that you might have for me. Bill? Yes?
How transferable is the information to other mine sites, the ratio?
So the idea behind this would be trying to set out site-specific optimization. So we're really looking at the procedure rather than the end game, right, or the end product, right? So it's the amount of effort and cost is fairly negligible to do this, certainly in the greenhouse context anyway. So with an optimization procedure, you would source amendments close to you. So it's going to, the ratio will change based on the particular amendment source and also the material that you're amending as well. They're going to have different issues associated with it. So you would find an amendment close to your source and then take that particular material that you're trying to amend and then set out to find the optimum. So those numbers, the optimum, transferability to other mines, probably I wouldn't take those exact numbers and do it. I mean, they'd be ballpark figures to start with, or to kind of set out a range of operating parameters. But ideally, you just kind of do your own optimization for your site. Yeah. Yeah.
Are you replicating the environment inside the greenhouse to match the environment at the site that you're actually trying to produce this?
No, and that's, I mean, it's very difficult to do in a greenhouse. But we are, we did the greenhouse work as a kind of a proof of concept. Does this type of design, will it yield usable results? So we didn't want to embark on a more costly field scale research program without really understanding whether or not these industrial statistical designs actually work. But they do work, in theory anyway, or it was quite effective in the greenhouse. At the quarry site that we're doing, we're taking that exact same design and putting it out to the field to see if the optimized amendment ratios will change. And with the tailings, we're just taking that optimized amendment and then playing around with the biological inoculants to see if it shifts, if we can get away with using like 2/3 or 1/3 of the optimized amendment if we add organisms. Yeah, so I mean, there's always going to be some issues with transferability between greenhouse work and field work, but greenhouse work is usually done to inform field work. Yeah. Anyone else?
So are you looking at how the vegetative cover will eventually affect the mobility of things like arsenic and mercury in the tailings below?
So with the greenhouse work that we did, we are analyzing the metal content, so looking at the mobile fractions of metal in the remaining tailings, and also what was taken up by the plant and then transferred to the roots or the shoots. So we're looking at the metals in the roots, metals in the shoots, and then the various fractions of metals in the soil. But eventually, in the field context, that in an ideal world we will, but I mean that's also dependent on funding and partners to do that as well. So I would like to do that. But certainly down the road, that's depending on grants, essentially.
Okay, I'm going to have to cut questions off there. We're getting close to lunch, so we still have one more speaker. Thank you very much, Greg.
Thank you.